All right, so this is a case where we studied the Miller indices for planes, and as we did for the directions, we also consider everything in here is being unity. All the sides of the crystal lattice we consider, and for simplification purposes. So even if they are not, as we know, most of them are not. So how do we, for example, if we have this problem when we have these two planes A and B, we want to write the Miller indices. So we are asked this problem in this way. So let's take the first one. As we did in the class, we talk about the fact that we have to find the intercepts first, and then we take the inverse, and then we get the Miller indices. If we have to reduce the fractions, we do reduce the fractions also. So in this case, we can see that the first plane is intercepting the axis y, in this case at 1/2. That's we see that there. It's kind of a little bit hard to see where it does intercept the x-axis. So we know that plane goes from minus infinity to plus infinity. So we have to take this side and continue with it until it intercepts the x-axis. And we can see that while here it moves on the y-axis, it moves with 1/2. On the x-axis is also moving with 1/2. So that's from this point to that point is 1/2. So that, and it moves on the x-axis with 1/2 in that. So it gets this intersection. So we continue that way. If we move with 1/2 in here on the y-axis, that it means that I would move in the same direction with a 1/2 on the x one. So I will end up at minus 1/2 right there, where it does the intersects the x-axis, which we put it there. And we also see that this plane is parallel with the z-axis, so we say that the interception will be at infinity. Now we take the inverse of these fractions that we get in there and the intercepts, and we get -2, we get 2, and we get 0. And of course, the Miller indices for planes, we said that they are in parentheses, round parentheses, and we put that negative in front of the 2, we put on top of it, and we call it 2 bar, and 2 and 0. So these are the Miller indices for the plane A. For plane B, we can see that it's easier to read the intercepts in here. The x-axis is intersected at 1, the y-axis at 1/2, and the z-axis at also 1/2. So we take the inverses, and it's much easier in this case, the easy situation. So now there are problems that we know the Miller indices, it's the inverse problem, so we have to, in this case, draw the plane. So how do we do so? So it's the inverse process like we did for the directions, same way. So in this case, we take the inverse of Miller indices, which we have it in here, to get to find the intercepts. So we can see that if this is 1 to 2, then the inverses of that will be 1, 1/2, and 1/2. So we get the intercept. That means this is the x-intercept at 1. The y-intercept is at 1/2, and the z-intercept is 1/2. And then we draw the plane between all 3 points. Very simple, that case. But it comes situations like we don't have a situation in here. Well, we do have that situation with a negative one. So when it's a negative, in that case, we either continue like we did here. We have to continue outside of the crystal lattice to find that way. So we have to kind of move ahead with that beyond the crystal lattice in order to find out when we have negative value, or we can use the technique that we said we move like we did for the previous case in the previous video with move the origin. So if this is the case, a peculiar case, you can see 3, 2 bar and 2. So in that case, that -2 there, it means that we have to find a new origin if we want to draw the plane in the crystal lattice. Otherwise, we have to draw it between various lattices, and it's not hard sometimes, but complicated, and it's not that intuitive. So again, the same situation. To find the intercepts, we need to get the inverse of the Miller indices. So in this case, we get 1/3 minus 1/2 and 1/2. Then we can see that at this moment we have this negative, only one. So that means that I can move my y, which is along the y-axis. So I can move my origin with 1/2 in the plus 1/2 direction, like there. So I put my origin right here on the y-axis on 1/2, and if I have to draw from the new origin the negative 1/2, I will stay within the crystal lattice. So I will go negative 1/2 in here. I can't do that. And because this is the only one, I'll select the origin on the y-axis. If I would have another minus 1/3 in here along the x-axis, then I will have to move my origin right here at plus 1/3. So I'll move 1/2 in the plus direction of y-axis and 1/3 in the plus direction of x-axis. But as it is, we leave it like that. And then after we shift the origin, we have the new origin selected. So now we are drawing this, as we said, for the intercepts at y-axis, x-axis, it will be 1/3. So as you can see, in this case, and I think I didn't move 1/2 in there in the positive. So it's, as you can see, it intercepts the x-axis, the new x-axis at 1/3 right there. That's one intercept. The y axis is intercepted of minus 1/2. Again, this is the new origin, so I will go minus 1/2 in this direction. And then the z-axis I will go, which is this, and I apologize, I just found a mistake in here. So that is not, that's supposed to be z prime. So because I still have y here. So you can see that I will go with 1/2 along the z. So that's where it intercepts. So I have this point B, this original index, that there. The bottom line is that I do have this 1/3, this, and the question is how you draw this after we put. So we have that one right there, and we set this point here. So you can see that if we unite these ones, we are staying in the new frame. But you can do all the way to find these intersections with the cubic lattice. That's where it's important for us. So if I take this instead of stopping short here and then unite with B, then you can see that so I will go all the way to C here and all the way to B and there. How am I mean, sometimes this is a weird scenario, not very simple. How are you convinced that we did draw the plane, the real plane, and we didn't make any mistake? As we talked in the class, we recalled that for the cubic system, only for the cubic systems, we said that the 3 to bar 2 plane will always have a perpendicular direction on it that has the same Miller indices. So which in this case is 3 to bar 2 direction will be perpendicular on this plane with the same Miller indices. And most of the time it's easier to find the direction. So if this is our plane here and this is our original frame there, XYZ, and then we saw the plane are intersecting. We have these 3 points, O, B, and C. We can take any other points, as a matter of fact, but suppose we have this, and these points have these coordinates. This is the origin, the first origin, and this is point B. Easy to find the coordinates there. Again, here sometimes we wonder how in the world, what's the point where this ends, because we knew that this is 1/3 here. But you can see that while on y-axis we run 1/2, here on the x-axis, along the x we run 1/3. So if from here I run another 1/2, then I should run another 1/3 in here. So I end up with 2/3 there, and that's will be 1 for this along the y-axis and 0 on the z-axis. So if you know I have these two vectors, and the direction that's perpendicular on this OB and OC is supposed to, we find that vector is the cross product between the two. Maybe you recall this from the physics or the statics classes. So easy to write if I have this. So you can see that I have the coordinates there. So I am gonna, for OB, this is how we put the cross product. So the vector OB will be 0 minus 0. I mean, it will be this, as you can see, I put the coordinates there. And the vector OC, again, the coordinates are there. So now we are solving it, and this is a determinant that you guys probably, I own, it's beyond the teaching you how to solve it, but the first one, it'll be I, as you can see, and I have this diagonal minus this diagonal, the product along these diagonals, and I end up with the minus 1/2. And then for the second, it's a minus j. Again, you have to know how to solve this. It's beyond the purpose of this video. So again, I have 0, and here I have minus 1/3, and then k. So you can see that we end up with these coordinates, I mean the components along the three directions. And if we want to match, of course, I need to reduce fractions, and I either consider 6. If I consider plus 6, I will end up with 3, minus 3, 2, and 2. Minus 2, pardon me. Minus 3, 2, and minus 2. But it's a direction that is parallel with this one, as a matter of fact. So I can use as a common factor minus 6 instead of plus 6. So in that case, I will end up with 3 minus 2 and 2, which we put it there. So we get the same Miller indices for the plane. If it wasn't to get the same, if I made a mistake, I will not get the same Miller indices. So I hope this helps, even for the peculiar cases. We didn't solve for all peculiar cases, but it's just for a little bit so you can see. This is, I'll leave you with the test in the end. So if you go through this, let me know if you got the right conclusions. If you don't don't know how to do it, then please send me an email and I will give you the solution. I hope you have a beautiful day.